Okay, so you are able to see my screen, and this is what we had done in the last class. So let me start, let me just quickly go through it. So what we had done is we had introduced matrices, and
Sir, you are on mute.
Sir, you are on mute.
We cannot hear you, sir.
can you hear me?
Yes, sir.
Yes, yes. Now you're.
Yes, sir.
Okay, so I don't know, there is some problem. Was I thrown out of my own meeting? I don't know what is really happening. So the recording is on. Okay, fine. And you are able to see the screen?
No, sir. No, sir.
No.
No. No? Okay, so maybe I'll have to start. So share, share screen. I think now you can see that.
Yes.
Yes, sir.
Okay, so let's start to do this. So we were talking about matrices, matrix addition, uh, scalar multiplication. We showed that the set of matrices with this matrix addition and scalar multiplication is a vector space. We sort of came up with a basis for this vector space. So the basis was these matrices Eij. So this is how we define these matrices. So that was the basis, and we saw that these matrices are actually nothing but generalization of these unit vectors. And we defined an important matrix which is identity matrix, and we defined matrix vector multiplication. So what is the matrix vector multiplication? So you have a matrix, the matrix is written in this particular format, and you look at the rows of this matrix and you have this particular vector b. So if you are looking at the product a times b, then you look at the rows of a and take inner product of rows of A with the column vector B. So each entry is this. So the first entry of this product Y, if you want to call it Y, is equal to this. So this is vector Y. And now you have to specify the vector Y by giving its entries. So the ith entry of Y is basically AI transpose into B. That's how you will get the ith entry of this Y. So this is what you can see. So this is how we define the matrix vector multiplication, and this matrix vector multiplication we saw has a very interesting property, namely a of x plus y is equal to ax plus ay, and a of alpha x is equal to alpha times ax. And reason why these two properties hold true is basically these two properties hold true for the inner products also. So because the entries of the vector are nothing but inner products, these properties hold true for this. So in general, this superposition property we concluded holds true for matrix vector multiplication. This superposition property, that is property which is a defining property of linearity. So that's where we will start today. So that's what we want to do. So let f from Rn to Rn be a function, then f is called linear. So f is called linear function if for every alpha beta belonging to R and x y belonging to Rn, f of alpha x plus beta y is actually equal to alpha f of x plus beta f of y. If that holds true, then we'll call the function f to be a linear function. Okay, so that's the definition. And what is the first example of linear function? The first example of linear function is fix a matrix A in R m cross n. Okay, so please note how I'm fixing the matrix A. Okay, so this m is coming here and this n is coming here. Okay, and that's how I'm fixing the matrix A. So if I fix the matrix A as a matrix A in m cross n, then I can define a function f sub A from Rn to Rm. And how do I define? Fa of x is actually equal to Ax. And what is this Ax? This Ax that I have written here is a matrix vector multiplication we define. So that is what we have. So what do we have to verify? We have to verify that Fa of alpha x plus beta y is actually equal to alpha into Fa of x plus beta into Fa of y, which is same as saying check whether A of alpha x plus beta y. So this is same. So this thing is same as checking whether this is true. But this statement is something that we already verified in the last class. Because this is already done in the last class, so we already know that if you fix a matrix A, and with respect to this matrix A, if you do this operation, then alpha, so this function fa induced by the matrix A is actually a linear transformation. Okay, so that is something that you already know. So another example of linear transformation I want to look at. So that is from Rn to Rn. Let us consider okay, so instead of writing it in this form, I'll write, so suppose x is the vector x1 up to xn, then x1, x2 up to xn, this vector is going as xn, xn minus 1 up to x1. So do you understand the linear transformation x1, x2, xn? So this is the function action. Okay, so the question is f linear? So what do you think? Is this function linear?
Yes, sir.
The function is linear. So how do you check the linearity of this function? Any thoughts on how do you check linearity of this function?
So we write the final in terms of the initial.
Can you say it once again?
So like xn is equal to a0, a1 x1 plus a2 x2 plus a3 x3 kind of thing. You'll write n
Correct.
equations like that
Correct.
and like check the matrix after that.
Which matrix? So I have not talked of any matrix yet. I'm just telling you how the action of function is. So the vector x is sort of reversed. Okay. So what is happening to vector x? Given a vector x, I write its components as x1 up to xn. I reverse the components. That's what fx is. So is this a linear function?
So we can apply
Like,
superposition.
Yeah. So you have to check the superposition principle. So does superposition principle satisfy?
Yes, sir.
Yeah, it satisfies. You can check. But I will define a matrix. Okay. So let me define a matrix A, which is like this. Do you understand this matrix? Do you understand the matrix A I have defined?
yes.
Yes.
You understand it, right? So if I want to denote it in notation, then what is the notation?
Inverse of identity matrix.
Huh?
Inverse of
Inverse what?
identity matrix.
What is inverse? I have not talked of inverse. And if you are meaning the normal inverse, then identity matrix is its own inverse.
Sir, Aij is equal to 1 only when I plus j is equal to n, otherwise 0.
Correct. So that is one description, or do you see the description that I wrote here in terms of unit vectors?
Yes, yes.
Does
Yes.
that make sense? Is that okay? So this is like row description. If I want to write column description, I will write it like this in terms of columns. So these transposes are basically the rows. So I'm talking of first row, second row, nth row, and here I'm talking of first column, second column, nth column. Does that make sense? So this is what the matrix A is. And will you now agree that this action that I am speaking of is actually same as x going to ax for this particular matrix A? Do you agree?
Yes, sir.
Yes. So can I say that this linear transformation, this transformation, I think you all agree that this is linear. It's easy to check superposition principle. But this transformation that I am writing here is arising due to matrix vector multiplication. And what is the matrix vector multiplication? The matrix A that you define in this particular fashion and x going to ax. If you take this particular action, then in the previous page we already have shown that if there is a function which arises because of matrix vector multiplication defined in this particular way, then it has to be linear. So this function also has to be linear, right? So f is linear. Check superposition principle. Or the second way, what is it? Find the matrix A in Rn cross n such that the function can be described by action of A. Correct? So that's another way of proving. And I think the first way, checking superposition principle, you can do on your own. And the second way is actually done here. Okay. I have just produced a matrix A, and I have shown that you can write down the function as matrix vector multiplication. So is this example clear? Why this function is a linear function?
Yes, sir.
Okay. One more example.
Sir,
Yes.
sir, in the previous slide, sir, before this also.
Yeah.
Yes, sir. In this slide, you have written that f is a function that maps Rn to Rm, and it will be called linear if alpha beta belongs to Rn, xi belongs to Rn. So, sir, in this particular case, we are not taking we're taking into account the dimensions, but we're not taking into account the values. So the values could be transformed in such a way that it could become linear while getting transformed from one dimension to the other, right?
What do you mean by not considering values?
So, sir, as in like Rn is basically a real number space, right, sir? And Rm is also real number space. So we are saying that we're transforming from n to m.
Yeah.
But we're taking that the dimensions into account, but we're not taking the values into account. I mean, the values could be anything.
The
So,
values will be taken into account by these equations, no?
yes, sir. Yes,
So
sir.
that's where the values are coming into the
Yeah,
picture.
yes, sir. Understood. Understood.
Okay.
Yes, yes, sir. Thank you.
Yeah. So one more example. So let us consider vector x1 up to xn. Okay. And I will consider n to be strictly greater than m, greater than or equal to m if you want. So do you understand what I did? That's the action of f. So what is it doing? You consider a vector x. So x is the vector x1 up to xn. And I'm considering n is greater than or equal to m. And x1 up to xn goes to x1 up to xn. That's the action of f on the vector x. Do you understand the function?
Yes, sir.
Yes. So maybe I will give an example R4 to R3, x1, x2, x3, x4. That is the vector. Under F, it goes to x1, x2, x3. Okay. Is this a linear transformation?
Yes.
Yes, sir.
It is. Why?
So
We can
for
take
the
That
n
E1,
minus,
E2, E3 and 0.
huh?
We can take the vectors of A as E1, E2, E3 and 0.
So you are considering, so you are telling me you can represent this action as a matrix vector multiplication. Is that what you are
Yes,
saying?
sir. Yes, sir.
Okay. So now you have to give me a matrix which is in R M cross N. Okay. So that's the matrix you have to give. And how will you write down matrix A?
E1 transpose, E2 transpose, E3 transpose and 0.
No. So I want it of the size M cross N. So can you tell me what is the first column? I'll write down the N columns. What is the first column?
it will be E1 transpose up to EM transpose, and then the
No, no.
remaining will be 0 up to N.
Listen, when you're talking of transpose, even transpose, you are telling me first row, second row, and so on and so forth. I'm saying, can you tell me first column, second column, third column? So what
Yes,
should
sir.
be
So that
E1?
would be
1000.
yeah.
So
So
E1.
it will be E1, E2, E3, but all will be R4 and then nothing else.
So in M and N, what will you have?
There will be
Up to En.
Up to
En.
E
M,
M.
M.
Mumbai, M.
Then
Then nothing. Close the. Then there will be nothing after that.
that's it.
Yeah.
So
Zeros,
what is the size of the matrix?
zero column vectors, n minus
This
1
is
column.
N cross M. E will be Rn.
This is what? So EI which space belong to
Rn.
N.
N.
N. That is what you have.
Yes, sir.
So what is the size of this matrix that you have given to me now?
This is n cross n.
N cross N. So will a N cross N matrix give you access from Rn to Rm?
Sir, it should be E1, E2 up to En, right? That then only we can get M cross N.
So do you need, so think about it once again. So this is not the correct answer. So
Yes,
this
sir.
is not correct. So this will not work because it will send M vectors to N vectors, right?
Yes.
What do we want? We want N
M.
vectors to go to N vectors. So the size of the matrix has to be M by N,
Sir,
right? M by
E1T to EMT, sir.
So it should be E1,
E1T to
E2 up
EM.
to En.
No, no,
And
no. That's what I'm saying. You tell me in terms of columns. You are
sir,
telling
in
me in
terms of
terms of
columns,
rows.
it will be first column will be 1, 0, 0.
So that is E1.
Yes, sir.
What is second
Second
column?
column will be 0, 1, 0, 0, 0, 1, 0, 0, 0.
E3. Then
And sir, the last column will be 0, 0, 0.
0, 0. No, no. You tell me for Rn and Rm, not for 4 by 3. You tell me for Rn
Okay,
and Rm.
sir. Sir, the
Up,
first column will be 1, 1, 1.
1, 1, 1.
sir,
Yeah.
up to, say, we can write up to E1 to EM and rest are all zeros.
Em, then rest all are 0.
Yeah.
So these are 0 vectors, right? So
Yes,
you
sir.
are talking of these zeros as 0 vectors. How many of these?
N minus N.
N minus M. What is the size of this matrix now?
This is N cross N.
Huh?
M cross N.
M cross N. So where does this E1, E2 belong to? What is the length of the vectors E1, E2, EM?
M.
M
RM.
vectors. Okay, so these are all M vectors. So does that make sense now? So this is a matrix which is of the size M by N. And what does it do? When you multiply a vector, so you have E1, E2 up to EM and 0, 0, 0. You multiply it to a vector which is x1, x2 up to xn. What will you get? X1, x2 up to xm. So you have found out a matrix representation for this. And because there is a matrix representation, the function is linear, right? The function f is linear. So obviously, let us take one more example. Is this a linear function? Is this a linear function?
No.
Is this a linear function?
No, sir.
No, sir. No, sir.
No.
No,
Why is
sir.
it a
Does
linear?
not follow the superposition.
Okay, not a linear function. And why is it not a function? 0 is not going to 0, right? 0 vector should be mapped to 0 vector for sure in linear function. That's right?
It is also not following superposition principle, sir.
Yeah. So superposition, you take alpha is equal to beta equal to 0. Then what do you see? F of 0 has to be equal to 0. Correct? Yes or no?
Yes, sir.
Yes.
Yes. So if 0 is not mapped to 0, then definitely function is not a linear function. Do you agree?
Yes, sir.
So is it enough for me to observe that 0 is not mapped to 0? Where is 0 mapped to actually? Which vector 0 is mapped to?
1, 2, 3 up to
1,
n.
2, 3 up to n. Column vector 1, 2, 3 up to n. So the function is not linear. Is this function a linear function?
No, sir.
No,
Why
sir. X plus y
not
whole
linear?
square not equal to x square.
So the answer is not a linear function. Why?
Superposition principle is violated.
Superposition principle is not satisfied. Correct. So you have to check superposition principle. You see that superposition principle will not work. Where is zero vector going to, by the way?
Zero vector is going to 0.
Zero vector is getting mapped to 0, but in general, superposition principle is not satisfied. So this function f is not a linear function. So we have seen several examples of linear function, and one surprising thing for the linear functions was the following. Okay, before going further, let me take one more example because this example is really very interesting. Okay, so f direction by pi. So what am I doing? I'm saying f is a function from R2 to R2 and f sends every vector v to u. Okay, so how do you obtain this action? How do you describe this action? The way I describe this action is that where u is obtained from v by rotating the vector v in anti-clockwise direction by pi by 2 radian. So what do you have to say about this function?
So this is a linear function.
Why?
So because we can find a matrix A which will do the same. We can, in terms of cos theta and sin theta, we can find a matrix which will actually rotate it anti-clockwise.
Okay. Any other thoughts?
Sir, mapping means it's
Yeah, go on.
so mapping is in the same domain R2 to R2 only, so it is linear function.
So here also mapping was Rn to Rn in this particular example. Is it linear?
No, so it's additive means
Sir,
it should be vector
Yes.
space also. That's not. Sorry, sir, I cannot say.
Sir, V plus U is also rotated by 90-degree when F acts on V and U individually. So V plus U will be the same vector as F of V plus U. V plus U rotated by 90-degree will be the same vector as F V plus U.
So then what are you trying to say?
Sir, what I'm trying to say is, let's say we take two vectors V and U. So if we rotate individual V by 90-degree and then U by 90-degree, and then we calculate the sum, it will be the same as if we add those two earlier vector V plus U and then rotate by 90-degree. So it obeys the addition rule. Geometrically, I'm saying.
Okay. So any other thoughts?
it can be
So this
represented
function
by
is
the matrix 0, 1, minus 1, 0.
what is that?
It can be represented by the matrix 0, 1, minus 1, 0. Yeah.
It can be represented by the matrix 0, 1, minus 1, 0. Correct. So this 0, 1, minus 1, 0. What is it saying? You have a vector V. So this vector V is V1, V2. Then what happens? You multiply V1, V2 by this matrix A. So 0, 1, minus 1, 0 into V1, V2. What would you get? You would get V2 minus V1. So in the plane, what is really happening? If you have a vector V1, V2, so V1, V2 is here. What is happening to V1, V2? So this is V1, V2. So this distance is V1, this distance is V2, then you are having this distance as V2 and V1 negative. So how will the rotated vector look like? The 90-degree rotation vector will look like this, right? So here is the 90-degree rotation. And first component is V2 and the second component is minus V1. Is that matching to what you are trying to say? Divyam, is that matching to what you are trying to say?
Yes, yes, sir. So the first column should be 0, 1 and second should be minus 1, 0.
Correct. So first column should be 0, 1, second should be minus 1, 0. Then you will get what you really want to do. Correct? So you will get the vector by rotation of 90 degrees in anti-clockwise direction. And once you have that, so this is your V, this is your U. And because you are able to explain this action by matrix multiplication, this obviously is a linear function, right? So this is something that is really very important. So interesting. So far we have seen examples of linear functions. And what has happened in each case is that you are able to come up with a matrix representation. You are able to come up with a matrix A and you are able to define the action function f from x to y through some matrix multiplication. Y is equal to ax. That's what you are able to do. So the question, what is the question that I want to ask now? Can you tell me what is the question that I want to ask? So one thing I know, given a matrix A, belonging to Rm cross n, I know that there exists a linear transformation Fa from Rn to Rm such that Fa action A is going to Ax, or f of A into x is equal to Ax. Okay. So that's how I can define a function from a matrix A, and this matrix A will give rise to a linear function. So I know that. So this linear function is given by this. What is the question I want to ask now? So what is the question I want to ask now?
Sir, I have one question, sir.
Yes.
Sir, in previous slide, sir, can we say or can we conclude that if there is a matrix whose each vectors are linearly independent, then this function will be linear function? Because
Yes.
because in
Look at
previous
this example. Look at this example. The columns of the matrix are E1, E2, E3, EM, 0, 0, 0.
yes,
So are the columns linearly independent?
no.
But it still gives you a linear transformation, no?
So no, I am saying that if it is orthogonal, if it is already defined that there's that all columns are linearly independent, then can I say this is a linear function? Because in this case 0, 0, 0 is there, so it is not linearly independent, it is dependent.
Yeah, but it is still giving rise to a linear function, no?
Yes.
So I am making a much more general statement. What is the statement I am making here? The statement that I am making here is you consider any matrix A in Rm cross n. I am saying any matrix. So
Okay.
that matrix can be a completely zero matrix also. All entries are zero, no problem. that matrix also will give rise to a linear functional. What will be that? That will be f(a)x will be equal to 0, 0 vector. That will be the linear transformation given by A when A is entirely 0, right? It is
Yes.
still a linear transformation. So I am making much more stronger statement than what you are saying.
Okay.
I am saying that you take any matrix A, multiply it to a vector, you get Ax, fix that matrix, do this for all x, then this will be a linear transformation. Do you understand that?
Yes, sir.
Okay. So now what is the question I am really interested in asking? So you tell me what is the question we should ask at this point.
So if all linear function have a matrix associated with it.
Correct. So now we want to ask the converse question. Exact same converse question we had asked in terms of linear functionals in terms of inner product. We had said that inner product with a fixed vector A gives rise to a linear functional. The other question we asked in that case, the converse question we asked in that case was, if I give you a linear functional, can you represent it in a inner product form? So the same question I am asking now. So I have observed that if I fix a matrix A, then that matrix A will give rise to a linear function from Rn to Rm. If size of A is m cross n, then the linear function will be from Rn to Rm. So the converse question I ask is that if I am given a linear transformation f from Rn to Rm, can I have a matrix associated with that linear transformation so that I can say that matrix vector multiplication is only way of obtaining linear transformation. Exactly same thing that we did in one dimensional case. Linear functional, if you want to obtain, you have to come up with some inner product representation. So linear functionals are nothing but inner products. Same thing, linear functions are nothing but matrix vector multiplication. That's the characterization we want to look at. So the question we want to ask is that let f be a function from Rn to Rm, which is linear, be a linear function. Does there exist A belonging to m cross n such that fx is actually equal to ax for every x in Rn? And if that happens, then you will know that for any arbitrary function f, linear function f, you can write the representation, which is x matrix vector multiplication. So what are your thoughts on this? So how will you proceed to answer such a question?
So we will look where the basis vectors of Rn are transformed to Rn's Rm.
Sir, it is always not true because that basically means that there will be we will be solving simultaneous equations and we will be getting unique values for the matrix values, the entries in the matrix. So that might not always be possible. So I don't think so. This is.
Can you say once again, Debojay, na? You are.
Yes.
Yeah.
Sir,
So can you
if we have let's say we have a vector and we know the corresponding representation to that vector. Let's say we have a v and we have a u, and we multiply some a1, a2, a3 and whatever the dimensions are, and we actually solve the simultaneous equation. So it might not always be possible whether if we get a solution or not, right?
But
So
no,
we have
but
to get a solution in
what
order.
is this thing has to do with finding if there is a matrix representation or not?
So if there exists a metric representation, then A into V should give rise to U, right? So A can be some arbitrary weights. A contain some arbitrary weights, and then we will
No,
actually.
no. You are thinking in a different direction. No. That is not what we are asking. You are telling me whether there exists a solution to the system of linear equation. That is not what we are looking at.
So if there does not exist the solution of the linear equation, how will there be exist a matrix?
No, that is a different question. I'll come to that question and I'll tell you what it really means. So we will relate this thing to that question, but what you are saying right now is not correct.
So right now what we are looking at it if that function can be represented as a matrix form with a matrix operation.
Correct.
Also,
yeah,
we can check where E1, E2 till En are going to Rm space, like f of E1, f of E2, and f of En, and they will form the columns of the E matrix.
They will form columns of A matrix. Why? So, do you understand what Pulkit was just saying? Pulkit was saying that you look at vectors E1, E2, En. Is that what you are saying, Pulkit? They are all vectors in Rn. Then you take f of E1, f of E2, f of En. Is that what you are saying, Pulkit? So these are entries in Rm, correct? And now what you are saying?
Like we will form a matrix where the first column will be f of E1, second will be f of E2.
That's what Pulkit is saying. So this matrix at least has the same size as the size we desire. So this matrix has size m by n. And we also desire the size m by n. Okay, so the size is same. So Pulkit is saying this can be a good candidate for the matrix A. Abhay, are you trying to say something? Okay. So the question is why?
So yes, it seems like it's correct. Like in fx, if we replace x by x1 e1 plus x2 e2 plus till xn en, and as it is a linear functional, we can do superposition and break it in x1 into fe1 plus all of the vectors.
So you take x belonging to Rn, and I have x as form x1 up to xn. Then I can write x as x1 e1 plus x2 e2 plus so on and so forth up to xn en, right? So that's what I can write down. We have already seen this. You can write down any vector x as a linear combination of unit vectors. Unit vectors e1, e2, en in fact form a orthonormal basis of Rn. Okay, so that is something that is very good. So what you are suggesting is x1 e1 plus x2 e2 plus xn en, right? That's how you can write down. Then I consider f of x, so which is same as f of x1 e1 plus x2 e2 plus so on so forth plus xn en. And this thing basically because of superposition principle that f will satisfy, because f is a linear function, will be x1 f e1 plus x2 f e2 plus so on so forth plus xn f en. Is that right? Because f is linear, that is known to me. F is linear. So because of linearity of f, this is what I get. Now from here, what we are doing?
So here we know that FEI is belongs to Rn.
Correct.
So this can be written as a product of a matrix and a vector, where vector is x, x1, x2 up to xn, and the matrix is FE1.
Is that what you mean?
Yes, sir.
Excellent. So this f of x you have written in this particular form, where this matrix is A. These are m vectors, right? So this is an m vector. And how many of these m vectors are there? Total n, f e1 up to f en. So this matrix A is clearly in m cross n, the matrix that we wanted, and you are able to write down this in the matrix form. So what was the probably most difficult part? Probably the most difficult part for you was to go from here to here. The other things you should have already known. Why? Because we already have done exact same thing where in case of inner product, right? So you have to remember what we have done previously. Okay, you have to keep on revising these things because this is something that will keep on coming. Same thing is going to come one more time possibly when we talk of tensors. And at that time, I'll not even say these things or write these things. I'll just mention it and go ahead. So you have to be really careful about this. Okay, please don't forget what we have done so far. So this is exact same argument that we have learned so far, except for possibly the green arrow implication, where I wrote down this product as this matrix vector multiplication. Why? The way we have defined matrix vector multiplication, the way we have defined matrix vector multiplication is AX. So how we defined? We defined in terms of rows, right? A1 transpose, A2 transpose up to A M transpose, right? There are M rows of matrix and the vector is x1 up to xn, right? So that's what we had done. So this each row is of length n, and this xn is actually an n vector x1, x2 up to xn. No need to write it in terms of this. I can write this like this. That's what we learned, right? And then this is nothing but A1 transpose X, A2 transpose X up to AM transpose X. That's how we learned matrix vector multiplication, right? So this is how we understood matrix vector multiplication. So A1 transpose X, A2 transpose X, AN transpose X. But there is another way. There is another way of looking at this matrix vector multiplication. Okay, so what is that interesting way of looking at matrix vector multiplication? So this A1 transpose X, A2 transpose X, A3 transpose X, what we really get. So you have A11, A12 up to A1n, A21, A22 up to A2n. So that's the second row. AM1, AM2 up to AMN. That's the mth row, right? And each of them have size n. And the vector x is x1, x2 up to xn sitting here. Then how does the product really look like? The product looks like, so this is your A1 transpose times x, A2 transpose times x, and so on and so forth, right? So this is your A1 transpose. So A1 transpose into x, how does it look like? A11 x1 plus A12 x2 plus A1n xn. Am I right? That's the first entry, the inner product of first row with the column x. Then you have A21 x1 plus A22 x2 plus so on so forth plus A2n xn. That is how the second inner product will look like, and so on so forth. The last inner product, mth row, am with x, am1 x1 plus am2 x2 plus so on so forth plus amn xn. So this is how it will look like. So this is a vector. So this is an m vector. So this is an m vector, right? It has m components. So that's the matrix vector multiplication that is obtained. But because of the properties of addition of vectors, how can I write this vector as? Okay, so this is something that is really very interesting. So can I write it down in this way? A11, A21 up to AM1 into x1 plus A12, A22 up to AM2 into x2 plus so on so forth plus A1n, A2n, AMN into xn. And what is this matrix vector multiplication then really telling me? So this is column 1 of A. This is column 2 of A, and this is column n of A. And for a particular choice of vector x, meaning that some values x1, x2, xn, what am I really looking at now? I am really looking at that x linear combination of columns of A. That is the matrix vector multiplication AX. So this is something that is really very interesting, and that's what I have used here. So this is first column of A times x1, second column of A times x2, third column of A times x3, so on and so forth. So that's what I have taken. So if you see linear combination of certain column vectors, you can always write down that linear combination of column vectors as matrix vector multiplication. And what did you do here? You saw certain linear combination of columns FE1, FE2, FEN. So that you wrote in terms of matrix vector multiplication like this. So that's what we have done here. So that's Nikhil, what are you trying to say? Nikhil? Okay, so I think he is in singing mood. Let him sing, that's fine. So this is what you get. So I hope this interpretation is clear of matrix. Is it okay to everybody?
Yes, sir.
Okay, excellent. So I think it's almost time. So let us stop and discussion tomorrow. Is there anything that you want to say? You want to add to this discussion? Is there anything? This is going on YouTube, okay? Nikhil.
Sir, you can
I
you
don't know
can
how
mute
to
him,
mute
sir.
him.
Sir, just right click on his name and there will be option of mute.
Really? Mute participant. Thanks. This is very nice. I never knew of this option. Okay, so is there any doubt? Is this interpretation of matrix vector multiplication clear to you? So this interpretation of matrix vector multiplication is something that is really going to play a very crucial role in understanding whether a system of linear equations has a solution or not. Okay, so that is something that is really very crucial. So Debojay was asking something about whether there exists a solution or not and how that solution is related. So that solution is actually going to be related using this particular interpretation of matrix vector multiplication. So is there anything that you want to add to this?
Sir, do you mean to say that this A1, A21, A up to AM1 can be easily found out using FE1? Like this is something that we do not need to find. This can be directly.
So that's what, no. So I am just telling you how the green arrow implication is coming. How can I write down that as a matrix vector multiplication? So I am explaining that this is the reason why you can write down matrix vector multiplication. So that's all I am saying. So this is another way of looking at matrix vector multiplication. And this I am telling so that you understand this green implication. That's all. Okay, then if there is no other doubt, maybe we can stop. So, yes, Debojay.
Sir, actually, I have a problem in intuition.